All right, so we left off last time with sort of this troubling idea, but truth, that the D2 UV vis spectrum of D2 complexes is complicated because of electron-electron repulsion. Even though we appear here to have only one energy gap in the molecular orbital diagram, in reality, there are many different electronic states that can arise because of electron-electron repulsion. So we have to keep track of things here very carefully. In particular, we have to keep track of spin and the different possibilities amongst the different excited states. And in order to do that, we have to go back to quantum in order to do this. Okay, so remember, right, you know this from general chemistry, there's a principal quantum number N, angular momentum quantum number L that tells you what shell you are, right? 0, L equals 0 is an S orbital, L equals 1 is a p orbital, 2 is a d orbital, 3 is the f orbital, etc. That m sub L magnetic quantum number, that ranges from negative L to positive L, and that tells you, which type of p orbital you are or which type of d orbital you are, right? There's 7 f orbitals because you're going from -3 to 3, right? And then there's a spin quantum number, spin up plus 1/2, spin down -1/2. So, just as a review, what are the quantum numbers possible for a 3D shell? Well, that means n equals 3, principal quantum number. That's the definition, sort of what energy level you're at, what row of the periodic table you're at, right? L equals 2. This is a D, right? And then m sub L can range from -2 to 2. Those are the 5 d orbitals. And for each of those m sub L's, you can have a -1/2 or plus 1/2 spin down or spin up for m sub S. All right, so I think we're happy with that, right? And I think everybody can do those quantum numbers, even though you might need to review them a little bit. Now what we have to do is we have to introduce the concept of a microstate. The idea of a microstate is that in each shell, electrons can be configured in many different ways. They can occupy different subshells and with different spins. The specific combination, okay, of the subshell that they're operating in and the spin that they have, this is called a microstate, okay? Some microstates can be ground microstates, whereas others can be excited states. And a group of microstates with the same energy is called an electronic state. So take the example of D1, okay? You've got a fully degenerate D shell, like in an atom. So you have 5 d orbitals, same energy, 1 electron. Well, you can put this in 10 different microstates. Spin up in each of the 5 subshells, or spin down in each of the 5 subshells. Here are 3 different examples, but there's 10, right? And it comes from the 5 different subshells, and then the spin up and spin down combinations. 2 times 5 is equal to 10. Now, all of those, I think we can intuit, have the same energy. They all have, spin up or spin down, that's arbitrary, right? And they're just in different subshells. Well, all the subshells are the same energy, so that's arbitrary too. So all of these microstates are part of the ground state electronic configuration, right? We said a group of microstates with the same energy is called an electronic state. So all 10 of these different microstates are the same electronic state, and this is a ground state. All right, now things get a little bit more complicated when you have more than 1 electron. And so you can do some math, but it comes out, you're dealing with permutations and combinations. So whenever you're dealing with combinations and permutations, you always have factorial, right? That's your exclamation point. And you guys remember what factorial is? 4 factorial is equal to 4 times 3 times 2 times 1. 3 factorial is equal to 3 times 2 times 1, okay? So it's this formula where n0 is the number of degenerate orbitals and ne equals the number of electrons you're trying to put in. So for example, how many microstates are in the D2 configuration with fully degenerate orbitals? Well, there's 5 degenerate d orbitals, so n0 equals 5, and we're asked for the D2 configuration, so ne equals 2. So you crank through that math and you get 45. So we're up from D1 had 10, we're up from 10 to 45 now for D2. And you can crank through this math for all the different configurations. D5 is going to be the most gnarly. You have 252 different microstates. You can see D3 has 120, D5 has 45. Look at this. D1 obviously has 10. We did that. D10 is just going to have 1, right? Totally filled. D0 also has 1, right? Totally empty. D1 has 10. D9 has 10, right? Because you can have that one gap, that one hole in 10 different locations. So you can see D2 and D8 have the same. So the 10 minus n is the same as the n, right? In terms of the number of microstates. So there's some symmetry here in this table. All right, so let's now go back to this concept of the D2 complex, okay? What are we gonna do? This is a strategy that we're gonna figure out all the different states that are possible, and then at the very end, figure out the spin allowed ones and Laporte allowed ones or Laporte forbidden ones, however it may be. And from that, determine how many peaks there should be in the UV visible spectrum. So first, we're gonna find energy terms for electron-electron repulsion in a free vanadium 3+ ion under spherical symmetry. So we're gonna do things under spherical symmetry. This will just make the problem solving easier, okay? So I'm just giving you a guideline of how the problems are solved here. It just helps, you can do it other ways, but this is the easiest way. Then we're going to basically do a descent of symmetry. And we're going to determine how all these different terms change under octahedral environment, which is what we care about. This is an octahedral molecule, at least we're approximating it as such. Of course, there is going to be some Jahn-Teller distortion. And then we're going to determine which transitions are spin allowed. And from that, we will get the, we will make a prediction about how many peaks there will be. So in order to do that, our first thing here is find energy terms for electron-electron repulsion under spherical symmetry. That is an atom. It's a free atom. So we have to go back to term symbols for atoms, which I think you have learned about that in PChem, hopefully. And so there's a different nomenclature. You know, we talked about term symbols for molecules. Okay, so we're going to have to talk about this. Let's do that in the next